Good afternoon. It is an introduction to environmental engineering, water treatment section by myself. And the last 2 weeks before midterm examination period, we tried to understand what contamination we have prior to making drinking water. So we have a couple of different categories of contaminations from the particle and colloid and organic matter, ions, and microorganisms. So then we categorize this one in terms of size, in terms of the structure, in terms of and charge. So then we use those characters, properties. So we are designing what types of mechanisms and subsequent the treatment processes available to remove to make sure those waters are potable and safe to be used by citizens. So generally, water treatment area is the public sectors, but especially Korea and the Asian countries, mostly public sector. But Western country, especially European countries, they rely on the public, the private sector as well, industrial sector as well. So Korea, do you know who provide the safe drinking water to you, to citizen? Who provide? Who provide tap water, 수돗물? Yes, K-water. I believe more than half drinking water made by K-water. How about the other half? Who made those half of the safe drinking water? Okay, thank you. 배수지 is 배수지 is kind of the tools and reservoir types of the facilities, right? But my question is who, the authorities, or who is responsible to supply tap water to the citizens and consumer? So you only know the K-water. K-water is 100% supply tap water to the consumer. Do you think? Yeah, 삼다수. Yeah, that's good. So that's not the tap water, right? That's the bottled water, 생수, bottled water. So we have tap water, 수도꼭지 water, tap water. So who supplied that? Samsung provide? 삼다수 provide? No. LG? No. KT? No. And K-water and the other, who are the other? Government. Okay? So Daegu government, Busan government, Seoul government, they provide the safe drinking tap water to the citizens. So half responsible for safe drinking water, half K-water. So that's the major the supplier. Okay. So we have understood of these the size of this one. So these are the conventional treatment. So these are conventional treatment process to control particle and colloid and microorganisms. So first, the rapid mix. So then when you visit water treatment facilities, 정수장, water treatment facilities, 정수장, So we have Ulsan, of course, have Jeongsujang water treatment facilities. When you visit there, when you visit other city, when you visit the K-water, so they almost have these types of conventional treatment process train. So we use the terminology of a train. Train means series, connected facilities, connected treatment process. The first, rapid mix. Second, flocculation basin, flocculation, and sedimentation, sand filtration, disinfection, and then distribution. So particles, so please remind you of yourself, particle higher than in size, higher than which number? Magic number from the famous physicist Einstein, 0.45. Yes, thank you. Park Jung-in, thank you. So then we can wait to be removed. So then we have a colloid. So we would like to now colloid. The colloids are stable. Stable means they float in the water, never settled down, almost forever, like a coffee, like a clay. So then we would like to destabilize. We would like to destabilize. So then they combine. So we already know why they are stable, because of charge. Clay and colloids may have mostly have negative charge. Negative charge, they repulse each other. So they stable. And then we add coagulant, alum and iron, and to destabilize. Then with the destabilization process, they combine each other to make a bigger flock, and then settled down. So those are achieved in both rapid mixing and flocculations. Rapid mixing, we add coagulant chemicals such as iron and aluminum, and slowly mix to make a form, to make a flock, and then wait for a while to remove those flock. Okay. So here is we have so we have a colloid and colloid. They are stable. Why? Negative charge. They repulsed each other. Then we add positive charged chemicals, aluminum and iron. So when you visit there, so they supply, they means K-water or government person, government operator. They add aluminum iron to destabilize, make these types of what? Flock. This is bigger size of a flock. And then they come down to the bottom to be removed. So please look at this one. So please look at the left-hand side colloid. So here is a colloid in it. So so if you wait 1 minute, 2 minutes, 10 minutes, 60 minutes, and almost a day, a few days, never change. So colloids are the stable at the left-hand side the chamber. But if you add coagulant chemicals, please look at the right-hand side the reactor. So can you see some kind the flux, right? Some flux. If you wait a couple of minutes, these flux settled down. So that's the flocculation, coagulation process to remove colloid. Okay, so coagulant chemicals, aluminum-based one, iron-based one. We have two different types of that. Okay, aluminum-based, iron-based. Then they are positive charged. So remind the colloids have negative charge. Then they are stable. They can be unstable, destabilized with the addition of aluminum-based coagulant, iron-based coagulant. So Korea use aluminum-based coagulant mostly. I think China and Japan. I'm not sure Japan. So I never searched the usage of the coagulant. Okay, so but U.S. USA use mostly iron-based coagulant. So European countries, I think a mixed one. So Korea, which one mostly? Aluminum-based. How about the US? Iron-based. Which one is better, do you think? So they both. So aluminum and iron, both are positive charged. So iron-based coagulant is more expensive than aluminum. But there are other reasons as well. So I'm not sure you're familiar with these types of controversy. But the long time ago, USA, America stopped to use aluminum-based coagulant because they believe. So there are some the research paper out of the scientific research group, especially medical area. The aluminum may may cause of disease of Alzheimer. So we are hot right now with disease of Alzheimer. So the cognitions lower the disease. So 인지 저하증, right? So we don't want to call the person suffering from these types of disease. So cognitions, the lowered disease, 인지 저하증. So we've been called those patients the 치매 환자, but the 치매 is not the right words right now. So I'm not sure you yesterday. So Anthony Hopkins got the major actor prize from Oscar with his movie, The Father. So Father, deal with a patient suffering from cognitions lowered, the disease, so 인지저하증. But aluminum is a maybe major cause of this one. So we've been exposed to, so we are going to be exposed to the tap water with some levels of aluminum. So we may exposed to that types of disease. So we are not sure yet. Okay, this is still controversy. But the USA stopped to use aluminum-based one. So once again, aluminum-based coagulant is very effective to remove colloid, but be concerned. So we have to be concerned of the possible of causing to give us that types of disease. So that's why iron-based. Iron is more expensive. Okay, iron is expensive. The less effective sometimes, but America prefer to use iron-based coagulant due to that problem. Okay, so this one, so right after addition of the coagulant chemicals, so there are a couple of different types of rapid mixing. So if you add coffee powder in your cup, then you mix very rapidly, right? So that's the similar one. If you add coagulant, and then we have to mix those coagulant into water containing the colloid very rapidly. And then, so the following rapid mix reactor, we have a flocculation tank. Then we have also paddle. We have a paddle, but the slowly moving at this time. After rapid mixing, then we use the slow mixings. Why slow? Why slow? To make flock. To make a flock. So with the addition of a coagulant, we have destabilized the colloid. The colloid may form the flock, the bigger size of coagulations. And then if you use rapid mixing again, that flock may be broken. Then that's why we use this slow mixing, paddle types of mixing. Then we call this tank as flocculator. Okay, so then these types of flocculation test, then we wait. So you add the different types of dose we test, then to decide which doses, how many the chemical needed to make appropriate and suitable and optimum flocculations. So that's we use those jar test. Okay, so we experience rapid mix and flocculations. Then we wait, right? To remove at the bottom of the sedimentation tank, 침전지, sedimentation tank, 침전지, to remove from the bottom all the flock. Okay, all the flock, and then upper side of water of a sedimentation tank to deliver to the next step, which is rapid sand filter. So this is sediment flocculation and sedimentation tank. The flock removed at the bottom of that. Upper water flows through this where then deliver to the sand filtrations. Okay, so through those one, we believe we successfully remove the particle and colloid. Okay, what else do we have? We still have organic matter, right? We still have iron. We still have microorganisms. Bigger size of microorganisms actually removed through and together with the colloid at the flocculation and coagulation and sedimentation tank, right? But we still have organic matter and ions, and some small size of the microorganisms like a virus, like a bacteria. So now we have a rapid the sand filter. And then please look at the rapid sand filtrations. So a rapid sand filtration is nothing but this chamber filled with sand, filled with gravel. Okay, so you deliver your settled water. Okay, so this one from upper side of a sedimentation tank. So come into this sand filtration, filter through from the upper side to the bottom, and filter through to remove contaminant, potential contaminant. Okay, this is a sand filtration process. This one is a sand filtration, so typical reactor, typical reactors. So filled with the sand, and at the bottom of that, they collected the filtered water, cleaned water, treated water, and then we use this one to further process, to be distributed and to be delivered, to be supplied to the consumer. Okay, upper side we have treated water from sedimentation tank, filter through all the water down to the this pipe, and then we collected treated water out of sand filtration to make sure to remove potential contaminations. So with the sand filtration, I have a couple of the questions through this the sand filtration. So we may have a purifier. We may have a purifier, 정수기 at home. So if you open your personal purifier, then you can easily find the one filter is a sand filtrations. Sand filtration. Sometimes you can notice sand filtrations and activate the carbon, soot activate the carbon filtration. But in general, water treatment plant in US and Korea and other countries as well, we mostly use this the sand filtrations. Okay. What kind of contamination can be removed by sand filtrations? My first question is particle and colloid. Particle and colloid already removed, right? Already removed, but some particle and some colloid that still remain in the water. Maybe not, but maybe. So then we would like to make sure those particles and colloid removed out of filtration. So filtration is very efficient to remove remained very small amount though particle and colloid. Yes, which mechanism? Which mechanisms can remove the particle and colloid by sand filtration, do you think? sieving. Okay, 채가름, sieving. Sieving process. How about the organic matter? Do you think a sand filtration can remove organic matter? No. Okay, thank you. That's right. So we cannot remove organic matter, right? So organic matter, please imagine organic matter the size. So only 10,000 Dalton or 1,000 Dalton, very small. The protein and saccharide and lipid, those are very small. But sand filtration has pore, right? Sand filtration has pore. Pore size is much bigger than organic matter size. That's virtually we cannot remove organic matter at all. How about the iron? Do you think we can remove? No, right? No. How about the microorganisms, do you think? Microorganisms. Yeah, probably yes. Microorganisms, once again, bacteria. How about the bacteria size? Bacteria size, micron. 1 micron, 10 micron, 100 micron. So then, not 100%, but some actually removed by sand filtrations. Okay, the still sieving process and some microorganisms, especially bacteria, attach to the surface of a sand, attach to the surface of the sand. So that's the absorption process, right? Absorption process. So the sieving, sieving process and absorption process are major mechanisms for sand filtrations. So we are at rapid sand filtration. Why rapid? Why not slow? So even if you are not water treatment engineer, you are not environmental engineer, so we can imagine why sand filtration use rapid filtrations instead of slow filtrations. So if you feel the water very high, it is more effective. Yeah, that's true. That's true. If you feel it very high, then you push the water toward the sand filter in a higher pressure to make more water out of this one, right? So we may define that this one effective one. But if you feel the water very shallowly with a lower height, then the filtration, the speed, the water permeations, the speed is very low. Then we have what? Slow filtration. If you feel high height, then we have a higher velocity to filter through this the sand filtrations, but with lower levels of water, upper side of this sand filtrations induce lowered, very slow filtration rate, filtration velocity. But we have very slowed water, but removal efficiencies are higher than rapid filtrations. So effective means depending on aspect you'd like to see in terms of mechanisms, in terms of efficiencies, right? Okay, and sand filtration has another advantage. Sand filtration, so if you operate this sand filter in a slow way, in a slow rate way, then we can grow inside this sand microorganisms. So with the slow the filtration rate, microorganisms remove which one? Okay, my question is that let me ask you again. If you filter this sand filter in a rapid rate way, the velocity is high enough to not allow microorganisms, biological microorganisms to grow inside the sand. But if you operate in a slow way in terms of velocity of filtration rate, then we can have microorganisms inside this sand. We don't want microorganisms to drink, but inside the sand, they grow. They may grow. They consume what? They consume organic matter, right? Organic matter. That's the advantage from slow filtrations. But generally, both in Korea and the US and European countries, they use rapid filtrations. Okay, so that's the other questions. Okay, so after rapid filtration, so we almost not make sure any presence of contamination, though, but we make images almost all contamination from particle, colloid, and microorganisms, so could be removed from rapid mix, flocculation, sedimentation, and rapid sand filtrations. And then we have a final step before distribution. Final step before distributions, which is a disinfection. Disinfection is for killing or inactivating microorganisms such as bacteria and virus. 소독, the process. So even if you have some organic matter, it doesn't matter, right? So organic matter itself is not toxic, not carcinogen at all. And some ion, the sulfate, the phosphate, and some other ions are not toxic at all. So we don't have to worry about it sometimes, but we have to be careful whether we have the toxic ion. But generally, from Nakdong River, from Seomjin River, and other rivers and the lake and groundwater do not have any toxic ion. But once again, today, 2 weeks before the classes, so we already discussed the potential presence of arsenic in the groundwater and the Mekong River in Vietnam and Bangladesh and Taiwan. But in Korea, luckily, so we don't have those toxic ion in our groundwater and river water as well. So we are pretty ready to distribute those water to the citizens. But we would like to make sure we don't have any microorganisms. That's why we use disinfection. Okay, so disinfections, so we call those one disinfectant, 소독제, disinfectant and oxidant. What's the typical examples? What could be a typical example? First one, chlorine, 염소. The second one, ozone. And third, chloramine. The first one, chlorine. Second one, ozone. And chloramine. Please look at the efficiencies, how powerful they are. So which one is the first? Ozone. Ozone is most effective, most powerful oxidant and disinfectant. And the secondary, we have chlorine dioxide, ClO2, chlorine dioxide. Here is, and chlorine and chloramine. Okay, so and once again, with most water treatment plant, in Korea, US, European countries, okay, which one they would like to use? For disinfection. Which one? If you are engineer, which one do you prefer to use it? Ozone, right? Ozone. Okay, that's the best way. But in Korea, US and European countries, so China, so we are using mostly chlorine, 염소. So can you smell when you turn on your tap at home? 수도꼭지를 틀면 you can smell the chemicals, right? Those are chlorine. So we mostly use chlorine. Why chlorine? Not ozone. Can you guess? There are two different reasons. Okay, ozone is powerful. Chlorine is less powerful. But why we are using mostly in a water treatment plant in Korea? Chlorine. Okay, ozone is 온실 gas, global warming gas. Okay, that might be, but other reasons, expensive, right? The first reason is expensive, very expensive. Okay, chlorine is almost nothing compared to the price of ozone. There are other reasons as well. There are other reasons. Somebody guess? Somebody guess? Ozone expensive. Okay, that's true. Okay, once you add ozone disappear almost half after 20 minutes, which means half-life of this ozone, half-life is 20 minutes. And after a couple of hours, there is no ozone at all. There is ozone at all. But chlorine remain in water much longer times, couple of days. Okay. Not completely, but a couple of days. So ozone is powerful, very effective, very good the disinfectant and oxidant, but disappear almost spontaneously after insertion, right? And the hydroxyl radical is even powerful than ozone, but hydroxyl radical is a radical. Radical, a couple of seconds, they disappear. Okay, if you add hydroxyl radical, if you add water hydroxyl radical, they are very powerful to kill everyone, to kill every organisms, but they disappear almost the same time. The picosecond, nanosecond, whatever that is. But ozone remain, how long? Couple of minutes, right? Couple of hours, not hours, so 20 minutes and 40 minutes. We can actually anticipate. But chlorine, couple of hours, a few days. Okay, that's why we use chlorine. We use the chlorine. Okay, but there are pro and disadvantages as well. Okay, so we are going to that in a second. So if you add, okay, there are questions. Isn't staying in the water with the harmful? Which one? Ozone? Badra, you mean chlorine? Yes, chlorine is very toxic, right? Chlorine is toxic. So we add chlorine in a small amount. Okay, with a very small amount. Not harmful. But we're not sure that's absolutely not harmful, but below the limit, below which or above which we can actually harmful. We can hurt from being exposed to that levels of chlorine, but we add below those. So we add the chlorine and approximately at 1 ppm, 1 milligram per liter generally. So after 1 hour, or after 2 hours, the chlorine still remain, but they disappear. Then you drink water. Even at concentration 1 ppm. So they said, based on medical scientific data, we are not hurt. Okay, that's the C. Thank you for asking. Okay, so the chlorine is that much powerful, and we've been using those one for a couple of decades. Very safe, we believe. But there are one concern from the scientist and engineer. Okay, so please remember, so we have organic matter, right? Organic matter before disinfection. Organic matter is not difficult, not easy to remove, so we have still that organic matter, especially occurring at the nature, occurring at the forest, on the groundwater, we have a natural organic matter. So natural organic matter can react chlorine to produce disinfection byproduct. Disinfection byproduct. Those are carcinogen material. Okay, we will get to that in seconds. Also, so disinfection can be evaluated by log removers. So instead of using percentage removal in water treatment sector, with the water treatment area, we use log remover. Okay, I'm not sure why they use log removal instead of a percentage. But so you may want to know these types of terminology to understand what they say in water treatment area. Okay, so how about one log removal? Please look at this. One log removal is 90% removal. Two log removal is 99% removal. Okay, so one log removal is 90%. 90%, so taking this one, taking minus log, 100% minus 90%. Come up with this equation, come up with 1, right? How about 99%? 99%. So taking minus log and 100% minus 99%. And then come up with this 0.01, then 10 to the minus 2, right? 10 to the minus 2. And then we have a 2. We have a 2. That's the 2 log removal. How about the 3? 99.9 corresponds to 3 log removal. 99.99 percentage removal corresponds to 4 log removal. Understand that way. Okay, so you don't have to compute this one. This one is just the customs in the water treatment field. So which one is higher? 3 log removal and 1 log removal. Which one is high removal? Between 3 log removal, 1 log removal. 3 log removal. Yes, that's true. That's true. 3 log removal means we can remove some bacteria by ozone or chlorine by which percentage? 99.9%. Okay, that's good. How about the 5 log removal? How about the 5 log removal? Which percentage corresponds? Yes, that's true. That's true. Okay, that's true. Okay, you understand, right? So in your examination next week, these types of the questions, the combined with the conceptual disinfection, conceptual process will be given to you. So very the simple questions will be given to you, but you may think of some kind of connections. Okay. So this one is a disinfections. This one is a disinfections. With chlorine react with what? Natural organic matter. Chlorine plus chlorine and react with the natural organic matter produced disinfection byproduct like this one. The first one, trihalomethanes, THM, trihalomethanes. Tri means 3, right? 1, 2, 3. Halo means halogen material. Methane is methane. So trihalomethane means 3 of this methane substitute in the methane component, the backbone, as backbone, then produce these types of DBP. Why they produced during disinfections? Because there is natural organic matter. Okay, that's why natural organic matter itself is not toxic at all, but if it reacts with chlorine, then we have carcinogen, very toxic material, DBP, which is trihalomethane. There are another one, there are haloacidic acid as well, haloacidic acid. So haloacidic acid, HAA, is these types of that. This one, CH3, COOH. CH3, COOH is acidic acid, but 3 halogen material substitute from the reaction between chlorine and natural organic matter. Okay, chlorine is very, very good disinfectant. But if you have natural organic matter and organic matter in your water, we have to be careful. Not produce too much these types of DBP, 소독 부산물. Okay, 소독 부산물. Disinfection byproduct. Okay, you understand? 이 부분은 좀 중요해서 제가 한글로 in Korean summarize. couple of seconds. 여러분, 지금까지 만들어진 게 뭐 거의 다 안전했는데 소독을 꼭 해서 내보내야 돼요. 법적으로도 그렇습니다. 근데 소독을 하면 미생물이나 박테리아 같은 걸 죽일 수 있고 바이러스를 죽여서 좋은데 뭐가 문제죠? 지금까지 얘기한 거. 지금 우리들 물 안에 유기물이 있는 경우에는 유기물하고 반응해서 소독제인 염소가 DBP 소독 부산물인 트라이할로메세인 다음에 할로어시딕 산을 만들어낸다. 이게 이제 발암물질이라는 얘기입니다. Okay. Okay, Badra asked me, the professor, I did not understand the second reasons why ozone is not used. First reason is the cost, right? And the second reasons I didn't mention yet. So with the chlorine, we have disinfection byproduct, DBP, potentials of risk to produce these types of risky material, right? But ozone has another one, another possibility. Ozone has another possibility. Okay, please look at this one, the Badra. Okay, this is the second reasons. So with ozone is very good disinfections, right? And to kill bacteria, virus, and the most resistant microorganisms in an effective way, very effective way, rather than the chlorine. But ozone has another problem. With your water may have some levels of bromide ion, Br-, bromide ion is high. Then the reactive ozone, the potentially hydroxyl radical as well, hydroxyl radical at high pH, and then we can produce bromate. Bromate is another toxic carcinogen material, 발암물질, 독성물질, bromate material, bromate ion. Okay, this is the second reason why we have to be careful in using ozone as our disinfections, especially if we have what? Keep in mind, okay? So I promise to give you this problem next week. Bromide ion. When we have this, the bromide ion at a relatively high concentration, when we have this bromide ion, yeah, please think about. So generally, Nakdong River, Somjin River, Han River do not have too high, do not have a too high concentration of this bromide ion. But when, if something occur, we have this one. You don't know? Okay, think about other knowledge, other facts, and actually you can learn from everywhere in internet site. So you can refer to other paper and textbook, at the lecture from the YouTube. But so most important thing in my class, in this one with introduction, so I'd like to give you, or you may have, is the common sense or some kind of intuitive types of criticizing capacity as engineer and the scientist to decide which water is safe, which water is not. And sometimes we may have be exposed to the risky situations, the certain event, right? So ozone is very powerful, and Daegu. So the Daegu, and I believe Seongnam, and some other the water treatment plant, they use these ozonations. So because ozonation is very good oxidant and disinfectant, but they have to be careful when there is a high concentration bromide ion. This one is from seawater. Okay, seawater. Please imagine Nakdong River. Nakdong River has we have a barrier between river and the seawater. Nakdonggang Hagwon, barrier, right? Barrier. But long time ago, without this barrier between the seawater and the river water, so then tidal the flow induce the seawater into the Nakdong River up to the city of Gumi, the city of Daegu. So the Nakdong River diluted with the seawater. So a concentration of chloride ion, the bromide ion, Br minus, tremendous high. Okay. Then if we use the ozone for our disinfections, so we may produce very high concentration of a bromate. Okay, so we don't want to use ozonations, even if ozone is very good disinfectant. We don't want to with that case. Okay, so see, there is a CT concept in disinfections. The CT concept in disinfections. So then to operate the water treatment plant in an effective way, without any exceptions, without any the problem. So there are FM, the field manual, and the regulations to operate those water treatment. So that's the one item to be kept by the operator is a CT concept. C is a concentration and T is time. C is a concentration and T is time. So concentration of the oxidant disinfectant, chlorine concentration, ozone concentration, and time is a contact time. So CT is a high. What do you mean by that? CT is a high. What do you mean by that? So we have a more chance to kill bacteria, the water cleaner. That's right. In terms of microorganisms, bacteria and virus, right? So if your water, let me ask you these questions. If your water has some bacteria. And government and the field manual, water treatment textbook require CT requirement 100. CT requirement 100. CT requirement is 100 for bacteria. Okay, CT requirement is 100. Should be done. This is regulation and law to kill the bacteria. Okay, and the C. What's the unit of C? What's the unit of C? Milligram per liter. Milligram per liter. ppm. Milligram per liter. And time, minute. Okay, time, minute. CT requirement. CT requirement in Korean is the CT 요구사항. 반드시 지켜야 할 사항. 이게 정해져 있어요. 법으로 정해져 있어요. CT is 100, and then your chlorine, you add 10 milligram per liter. And the retention time is what? Is what? 10 minutes, right? 10 minutes. That's right. That's good. So to kill the bacteria, so already a lot of scientists, a lot of engineers did the experiment and come up with this, the CT requirement 100. 100. And then, so if you would like to use chlorine 10 milligram per liter, and then we need 10 minute contact time to kill that bacteria. Okay, if you add chlorine of 20 milligram per liter, what contact time should be? 5 minutes. Yes, that's right. Okay, the CT is 100, and then C is at this time 20 milligram per liter. T should be 5 minutes, right? So that's the very simple. So let me ask you, with the same bacteria, this bacteria, so we have a CT requirement 100. CT requirement 100. So at this time, ozone can be used. Okay, ozone can be used. CT is still 100. Please remind, CT is 100 still. So ozone is 2 milligram per liter. Ozone is very difficult, very expensive to use a high concentration of ozone. And then a C of ozone is 2 milligram per liter. And then how about the contact time? 50 minutes. Yes, that's right. Very good. Okay, so you understand. Any questions? So these types of questions will be given to you next week. Okay, any questions? So any of you do not understand, please ask me. Okay, that's good. Bromate is very toxic. So bromate regulation is almost 1 ppb levels. So we have a trihalomethane, THM. We have a chlorine DBP, which are THM, HAA, trihalomethane, haloacetic acid. Regulation of those are approximately 100 ppb. 100 ppb, but bromate regulation is 1 ppb. That much very harmful. Bromate is absolutely, you don't want to drink any bromate containing water. Okay, Thank you. So, and then the CT, so how about the, okay, thank you. So a CT requirement understanding once again, let me ask you, okay, the bacteria, between bacteria and the virus, between bacteria and virus may be included in our water. Which one is more stronger to the disinfections? Between bacteria and virus, which one is more powerful and stronger to resist against the disinfection, do you think? Bacteria, yes, bacteria is more powerful. Virus is weak. So, so we have one virus and one bacteria. The CT requirement for the bacteria, was 100, right? CT bacteria is 100. How about the CT for virus? Ten? Okay. Less than 100, right? Less than 150? Yes, yes. That's true. That's true. Who knows? So then, so here we have a virus. Virus CT value is lower than bacteria and the protozoa. The protozoa is the most powerful one. Bacteria is the second, and virus is last. So then we recognize we can we can notice those order by a CT value. Okay, so you understand this table right now. Any questions about? I already promised to give you these questions to you the next week. Okay. So we now ready to distribute our water into the pipeline, Okay. So if you're an engineer, please imagine this is this one. The last topic to be discussed today. So we remove the particle, colloid, and some portion of the organic matter, not much, but infiltrations step. But we would like to make sure there is no virus and bacteria and protozoa. That's why we use the disinfections using either chlorine and ozone, depending on situations we have. Okay, so we are pretty much ready. And then, so if you're an engineer now, do you have anything when you concern with your water before consumer citizens and drink your water? What kind of things you'd like to concern? Clean pipe, yes, that's true. That's true as well. Okay, what else? Clean storage, yes. Taste. Okay, taste. Okay. So you taste the tap water? Yes, that's true. That's true. But we have to be making sure of this one as well. Okay. What else? 여러분, sorry again, couple of seconds. 여러분 이제 법에 따라서 이제 다 수돗물을 만들어 가지고 내 보내야 되는데 혹시 신경 쓰이는 거 없으세요? 혹시 신경 쓰이는 거? Okay, ions and organic matter themselves are not toxic at all, right? As we already discussed, this one is not toxic. So why are you concerned? The sulfate, sometimes we need a sulfate, we need a phosphate, we need mineral waters. Okay, could you? Okay, I don't have any things. So there is no right answer, but I'd like to suggest us, so that us concern our water, because so only 7% drink our tap water, right? Korean people 7% tap water. Why? Why general citizen do not like to tap water without any further treatment? Smell? So can you smell a carcinogen? Yes, they might be. Okay, so you are engineer, so you are younger than me and you are smarter than me. So then you are going to be responsible for infrastructure of our society in near future. So citizens, they would like to drink the safe and clean, tasty water, even out of a tap, but they don't right now. So they don't trust the tap water. Why not? They? So instead of they drink bottled water from Samdasu and Jirisan and Env Eng, why not? So we provide those one. Remaining chlorine. So that's true. But remaining to the chlorine may be good news to protect inside the pipeline, right? Inside the pipeline, there may be the bacteria and virus in it, right? And then the chlorine, the further disinfectant those to make sure our tap water inside the pipeline and safe as much as possible to provide us safe drinking water. Even if with chlorine, we don't want to chlorine, but those one things. The pH, of course, pH is very important. So affect disinfections and taste, even if we are not that much deep levels of discussion in this class. This one is introduction to. Okay, so micropollutant, what are those? Okay, can you give me an example of those micropollutant? Okay, pharmaceuticals, yes, pharmaceuticals and endocrine disrupting chemicals, so 환경 hormone. So in our tap water even. So everything. So you are answers. I'm not answers. So you think about those everything. So if you design sometime, you may have a chance to design water treatment treatment plan for citizen in public purpose way. Then you design better way than present by. So I involved the water treatment and wastewater treatment plant a long time ago, before going to US to study. So I had to work for the consulting corporation to design the wastewater treatment plant at that time for 5 years. So Bucheon 하수처리장, Bucheon, and Sokcho and Jeongju. So I involved those projects to design the water treatment plant at the time. But we just follow all the conventional treatment plan. But you are young, you are digital generations, you are more smarter than me and our generation, I believe. So even if you are not interested in these types of that, you might be the part of a water treatment project, because water is sometimes life itself. to our baby, to your parents, to your wife sometimes. If she's pregnant, and so you'd like she drink tap water at that time instead of Env Eng. So a lot of conflict issues, a lot of hot topic in this one. Okay, so please understand. So we might have a micropollutant, we might have EDC, we might have an issue of chlorine, we might have a disinfection byproduct issue. A lot of different things occurring at the same time with the waters. If you go to San Diego, I already mentioned the San Diego people, the people use wastewater because they lack of water itself to make drinking water. Can you imagine? So Korea is a lucky country right now, but in near future, who knows? So we are lacking the water more and more. If you visit China, some part of China, Western China, so they absolutely lack of waters. They use the wastewater as well. They used up groundwater. If you visit the Saudi Arabia and Arab Emirate, so they use still groundwater, but they used seawater to make drinking water. Okay. And the crisis of the climate change, the climate emergencies, so we might have sometimes disastrous danger of water. Okay. So who knows? So that's why the knowledge everywhere. So knowledge is not important sometimes. Knowledge is still important, but not critical sometimes. So then I'd like you to have intuitive sense to catch knowledge as well as sensing or the common sense in terms of scientific way. That's my asking to you. So this is it for today. And Thursday, so we are behind, but we can catch up and we finish up these other issues and desalination as well. Okay, thank you for your attention. Have a good day.
감사합니다.
네, 고맙습니다.
감사합니다, 교수님.
네, 고맙습니다.
Professor?
Yes.
Do you have time? I have one question.
Sure.
Can you clarify more about the one equation? I will just type it on the chat.
Okay.
Log
Your name 이수인?
remove is equal to.
Okay. So 이수인 CT requirement가 100이라고 하신 거 맞죠? 이거는 그냥 예제를 든 겁니다. CT requirement가 꼭 100이라는 게 아니고 예를
I'm sorry, I cannot speak Korean.
No, this is another question. So let me finish.
Okay.
Yeah, thank you for waiting. 이 CT가 100이라는 거는 꼭 그런 건 아니고요. 뭐 꼭 그럴 수 이제 CT는 하나의 박테리아에 대해서만 그런 거거든요. 예를 든 겁니다. CT는 20이 될 수도 있고 5가 될 수도 있고 이렇습니다. 제가 아까 예를 들기 위해서 그렇게 한 겁니다. 예, 고맙습니다. Okay, go ahead for us. Badra?
Yeah, I typed the equation on the chat.
Uh-huh.
Log removal is equal to FCT. So what does it exactly mean?
Okay, yes. So I probably mistyped that. Log removal is okay. So log removal is efficiency, is how we can remove the bacteria and microorganisms, right?
Yeah.
Yeah, and then that's the log removal is influenced, affected by how much we have of a disinfectant concentration packed, and how much we contact those doses with the microorganisms. If you increase C and T, and we can also we may increase the log removal as well. That's why I wrote this equation.
I see. So is it connected to the thing that you were explaining before, like 3 logarithm is equal to 99.9%
Sure.
of removal?
Right. Yes.
Okay. Thank you
If
so much.
If you increase the C and T, then you can increase the log removal. 4, 5, and 6.
But I'm not really sure how this percentage, for example, like 99.9% is like equal to
3.
CT, like
Okay.
CT requirement, because CT is 100, but
Okay.
I'm not really sure.
Okay. So then you have a lot of data with the log removal and CT. Then you may have regression equations like that.
Excuse me? I didn't understand it.
Okay, so there is no this types of equation in a textbook and others. I wrote this one to give you understanding of relation between the log removal and CT. So if you increase CT, then you can increase log removal.
All right, got it. Thank you so much.
Okay, thank you. Thank you very
I was
much.
just a bit confused. Thank you so much for the lecture.
Okay, thank you very much. Have a good day. Okay. 예, 다른 분도 고맙습니다.